Okay, question 16. Which of the following series converge? So here's a list of series. Can we tell which one converges? Um, okay. Let's see. We have three of them. Um, hmm. So I'm gonna take a look at this series right here, and think about what. I'm trying to think about a couple of tests that I can use. Um, by comparison, pretty much, if I can. So this one, I'm thinking I can use a comparison test of sorts by just, honestly, just by looking at this right here. This degree of the numerator, the degree is 1, right? And then the degree on the denominator is 3. Um, so this right here would be similar to a series of n over n to the third, which simplifies to be a series similar to 1 over n squared. So by comparison, these two are similar. Um, okay, so I would think about using the limit comparison test. Um, by the limit comparison test, it pretty much just says, so I know that this one converges. Okay, so if I run the limit as n approaches infinity, let me write this out actually using some yeah. So, anyways, I'm going to compare this to the series of 1 over n squared. This series converges, by the way. It is a p-series where p is greater than 1, it converges. So then the limit comparison test, the limit as n approaches infinity of, we'll take n plus 1 over, oh man, it's taking me everything in my power to just not simplify this too much, but to try and explain it. That times by n squared over 1. So the limit comparison test says that given a series right here that you have, both series have to be positive, which both of these series are always going to be positive. If one series converges or diverges that you know of, so I know in this case that this is a series that's going to converge. If I run the limit of the ratio, so this divided by this one right here, which just, if you use the reciprocal, well, okay, if I evaluate this limit right here, well, this is to the third degree, and this is to the third degree. So by a process of, L'Hopital's rule, you'll get that this is going to be equal to 1. And if, by the limit comparison test, the limit as n approaches infinity of a sub n over b sub n is equal to some constant, and that constant is between 0 and infinity, then they both converge or diverge depending on whichever one you're comparing it with. So in this case, the comparison converges. We get a constant, so they're both series are going to converge. So this one converges. Um, um, in this problem right here, it would probably, this is nice, but if you can just see this by looking at that right there and seeing the comparison, that's a good thing. Yeah, if you know that this converges right here and that's what this is similar to, this is going to converge if you run the limit comparison test. So there you go. So I know this one converges. Now these two right here, I don't know if you guys remember the video that I showed you last week, but I just want to point it out that if you see factorials, a good test to run when you see factorials and powers and stuff like that, a good test to run is the ratio test. Okay, so if I run a quick ratio test, so the limit as n approaches infinity of n plus 1 factorial over n plus 1 to the 100 times by n to the 100 over n factorial. If you simplify, n plus 1 factorial over n factorial is n plus 1. Okay. So times by n to the 100 over n plus 1 to the 100. The degree on the numerator here is 101. you have this 100, but you are also multiplying it by this one right here. So this is a polynomial to the 101st. This is a polynomial to the 100th degree. So if you run its course, obviously it would take a long time, which we're definitely not going to do. But if you run its course right here, um, this value, it's kind of hard to say, but it's going to be like our first derivative here would be you drop the 101, right, and then it'd be n to the 100th term, and then in the denominator it'd be 100, and then you have n to the 99th term right here. But in any case, as you keep taking all these derivatives by L'Hopital's rule, you're going to get a ratio, right? And that ratio is going to be larger than 1. So by the ratio test, this is going to diverge. The ratio test says that if you run the ratio test, if your limit is larger than 1, then the series diverges. If it's less than 1, it converges. If it's equal to 1, it's inconclusive. But this is going to diverge. Okay, another way to think about it. I don't know if I actually can use that idea, but I think I'd probably need to spend a little bit more time thinking about it, but n factorial should be faster than n to the 100th. Obviously it is, because if you run the ratio test, the nth plus 1 term is going to, the ratio is going to be larger than 1, right? So n factorial is faster than n to the 100th, so yeah, the ratio is larger than 1, which means it's going to diverge. Okay, so this one diverges. So diverges, I know this one converges. This one right here, so if I do the ratio test, so the limit, you can kind of already tell. I mean, we kind of showed it here. I think n factorial is going to outpace 8 to the n, but I guess the ratio test will show that. So 8 to the n plus 1 over nth plus 1 factorial times by n factorial over 8 to the n. That's going to be the limit as n approaches infinity. You're going to have 8 on the numerator, and you're going to have over n plus 1 on the denominator. Because this right here simplifies to just be 8. These two right here simplify to be n plus 1. Degree 0, this right, if you apply the limit, this right here is going to be equal to 0, less than 1. Therefore, the series is going to converge. So there you go. Okay, which of the following series converge? So again, so let's take a look right here. They're giving the nth term here, which is nice. But so if we think about this, the first partial sum is 1. Those two added together is going to be 0. Plus 1 is going to be 1, 0. Yeah, this series is going to have to diverge, because as you add, if you take into consideration the partial sums are going to alternate between 1 and 0. So this diverges. Yeah. Okay. For the next one, you can, let's see. So you have 1, 1/3, 1/5, 1 over 2 to the n plus minus 1. So if you think about it, just write it like a series. So series over 1 over 2n minus 1, that's similar to the harmonic series, right? So the harmonic series being, that's, I'll say, similar to 1 over 2 to the n. That's a harmonic series that diverges. So diverges for this one too. This one right here, you can see that this one's a geometric series, timesing by 1/3. So times by 1/3, times by 1/3, so on and so forth. It's always timesing by 1/3. That's a geometric series where the ratio is less than 1. This one's going to converge. Yeah. Okay, there you go. If the series converges and a sub n is greater than 0 for all n, which of the following must be true? Okay. We got our work cut out for us here, I think, in this one. So, if the series of a sub n converges and all the terms of a sub n are positive for all n, which of the following must be true? So here it says that the limit as n approaches infinity has to equal 0. So this looks like the ratio test, right? Um, So the ratio test says this: if the limit as n approaches infinity of a sub n plus 1 over a sub n, if this is less than 1, it will converge. It doesn't necessarily mean that this right here is going to be equal to 0. If it does equal 0, then it does converge. But, I mean, for all we know, that the limit, the ratio could be 1/2. It could be 1/3. We don't know if it's going to be 0, though, so I don't think we can necessarily say that this is true. I don't think we can know for sure that's going to be 0. The absolute value so all the terms of our sequence, so this sequence right here, a sub n is equal to a sub 1, a sub 2, a sub 3, a sub 4, so on and so forth, is less than 1 for all n. I don't know by what, I don't know if there's any indication that that is true. We just know that all of them are positive. We don't know if all of them are going to be less than 1. So I don't know if we can really say either of those ones right here. So it's saying that the series is equal to 0. I don't think we have any indication on what it's going to be. It converges. It can converge to 1. It can converge to anything. It doesn't have to converge to 0, so that doesn't make sense. Right here we have the infinite series n times by a sub n diverges. So if I multiply this by n, it's going to diverge. I don't think we can know that for sure. We do know that this converges. If we multiply that by some constant of n for each term, yeah, I don't think I can say that for sure. I'll keep this in mind, but it's kind of convincing if I multiply it some constant. So if I multiply series by n would be the it's hard to say. I'm gonna look at this one though. So we have the infinite series a sub n divided by n converges. This one makes more sense in line of what it says right here. So I do know that the series of a sub n converges if I divide each term by n, making each term smaller when I add up the series, then definitely that's going to converge as well, because this alone converges, right? So this one kind of is tempting, but again, it kind of depends on n. But this one I know for sure would have to converge, because if the series of a sub n converges, and if I'm dividing each term of a sub n by n, making each term smaller, then definitely that one would have to converge for sure. So I'd say E makes the most sense here. A lot of these ones don't make a lot of sense because it's just like making it I don't know. It's trying to assume something, which we can't say for sure on all of those. So yeah, I'd go with E. So if 0 is less than b sub n is less than a sub n, for n is greater than 1, which of the following must be true? So basically what this is saying is that you have a series of a sub n. So a sub n will be equal to a sub 1, a sub 2, a sub 3, so on and so forth to a sub n. B sub n, which will be equal to the first term of b, the second term of b, third term of b, the nth term of b. So for every n is greater than 1, this term will be larger than this term, and then these are all positive, so all these are greater than 0. This term will be greater than this term, so on and so forth. Yeah. Okay, so let's see. So if the limit as n approaches infinity of this one, so the terms of the series, if this right here is going to eventually be 0, then this series right here is going to converge. This is like the nth term test right here. And the nth term test proves divergence, not convergence. So nth term test, if the limit as n approaches infinity of a sub n does not equal 0, then a sub n diverges. So here's the thing. The limit as n approaches infinity of a sub n might still be equal to 0. If it's going to converge, then it's likely that it will be equal to 0, but this doesn't necessarily prove that it's going to converge. So that's why I'm having struggles connecting those two together. Okay. Let's read the next one. If this series converges, okay, so then the limit as n approaches infinity b sub n is going to be equal to 0. So if I know for sure that this one converges, then it's more likely that we can probably say that the limit as n approaches infinity of a sub n is going to be equal to 0, right? But the reverse does not mean that it's true, if that makes sense. So then if this one converges, then the limit as n approaches infinity of b sub n, the limit of these ones, well, if this one converges, then by comparison this one would have to converge, right? So then the terms, it makes sense that the terms of this would go to 0. So I'm liking this one, but let's read on. So if the series b sub n diverges, so if this diverges, then the limit as n approaches infinity is equal to 0. Then the terms are going to be equal to 0. No, I don't think we can say that for sure. We don't know. I don't think we can say that for sure. Especially if this one diverges, it wouldn't make sense that the terms of this would go to 0. It definitely wouldn't make sense for that. So I'm going to say no for C. If the series of a sub n, if this series diverges, so this one diverges, so meaning that the terms, that would mean that the terms right here keep getting larger, then this one diverges. We can't say that for sure. We don't know. If this one diverges and this one right here is less than, we can't say for sure if this one diverges. Definitely not. There's no, yeah, you can't compare those. If b sub n converges, so meaning that there's a finite value, then a sub n converges. Now, these are stating the comparison test in the wrong order. So, not those ones. It's stating the comparison test incorrectly, not in the order that we want. If this one, which is larger than this one, converges, if a sub n converges, then this one converges, given this inequality right here. If this diverges, this one also diverges because of this inequality. This is saying the opposite, so those are definitely not it. So again, I don't think this makes sense. The one that made most sense to me was this one right here for B. So again, let me just kind of clarify. So if a sub n converges, so this one right here converges, okay, then the terms of this one would have to go to 0. That makes sense, yeah. If this one converges, then the limit as n approaches infinity, that's going to have to be equal to 0. But again, you can't prove that. You can't use that to prove convergence, but if this is going to converge, then the terms would have to go to 0. Okay. Oh my gosh. This is so long. Sorry, guys. Let f be a function given by f of x is equal to 1 over x natural log of x for x is greater than or equal to 3. F is continuous, decreasing, and positive. So these right here are the requirements to use the integral test. So keep that in mind. Use the integral test to show that the series diverges. So, okay, that's easy. So we'll run the limit as n approaches infinity. The integral from starting with 1 to, we'll say x, we'll say n, sorry, of 1 over x natural log of x dx. I'm going to use substitution. So I'm going to say let u be equal to the natural log of x. Du would be equal to 1 over x dx. Dx would be equal to x du. So then I'll have the limit as n approaches infinity of the integral from 1 to n of 1 over x times by u times by x du. Those are going to cancel. So I get the limit as n approaches infinity of the integral from 1 to n of 1 over u du. Use the antiderivative. Limit as n approaches infinity. The antiderivative of 1 over u is the natural log of u from 1 to n. I'm going to undo my substitution. So the limit as n approaches infinity of the natural log u was the natural log of x, so natural log of x, and this is going to be from 1 to n. Limit as n approaches infinity of the natural log of n minus the natural log of 1. This right here is that's not going anywhere. That is like kind of an undefined expression, I think. The natural log of 1 is 0, and natural log of 0 is undefined. Okay? That's not going anywhere. This right here would be infinity, because if I evaluate the natural log as it approaches infinity is infinity, and the natural log as it keeps growing. So natural log is an increasing function, right? So this diverges. So this right here will just be equal to infinity. So this diverges. I guess I should say this right here. Let's be a little bit better. The integral diverges. So the series diverges. Okay. Should I finish off this question? Sure, I'll finish off the remainder of these questions and do the last part in the last video. Okay, so consider the infinite series given here, and that's what this infinite series is. Identify properties of the series that guarantee the series converges. Explain why the sum of the series is less than 1/3. So this is an alternating series. You can kind of see that from here. You can also see that go from positive, negative, positive. So it's an alternating series. Okay. And since it's an alternating series, let's use the alternating series test. So the terms decrease in absolute value, right? So the terms keep getting smaller, and so we're using this right here. So the limit as n approaches infinity of x approaches infinity of x natural log of x, that's going to be equal to 0. So I guess we'll state that terms decrease in absolute value, and the limit as n approaches infinity of 1 over n natural log of n is equal to 0. So those are the properties that make this converge. And explain why the sum of the series is less than 1/3. Well, so here's the thing. So the sum of the series, whatever the sum of the series is, right? Um, sum of the series. Well, okay, so think about this right here. If this is my first term right here, this right here and this right here, when you combine these together, this right here is less than this right here. This right here is less than this term right here. You add these together right here, pretty sure you're going to get something that's less than this right here. So then, with that being said, if you keep doing that, the most that this series can be, the series, the sum has to be less than this term right here. So my sum has to be less than 1 over 3 natural log of 3, for sure. Because you're going to keep chipping away at something like this right here, but it can't. But it's also always going to be positive too. So that is the most that the series could be, right? And that right there, this is less than 1/3. So explain why the sum of the series is less than 1/3. There you go. Okay. It's also kind of just using the alternating series error bound, right? Most of the series could be is this one right here, and that's less than 1/3. So, okay. Find the interval convergence for this power series. Show the analysis that leads to your answer. So if I'm finding the interval convergence, this is a power series. I'm going to use the ratio test. So the limit as n approaches infinity of absolute value of x minus 2. If I plug in n plus 1, that's going to become n plus 2 divided by n plus 1 to the natural log of, or times by natural log of n plus 1 times by n times by natural log of n over x minus 2 to the n plus 1. Okay, so let's simplify this right here. Those right there, if you subtract their exponents, n minus n is going to be 0. 2 minus 1 is going to be just 1. So absolute value of x minus 2 on the outside times by the limit as n approaches infinity. Let's see. We're going to have n over n plus 1 times by the natural log of n over the natural log of n plus 1. This whole thing right here is going to be 1. Look at the powers here. These are also similar functions. So it's like, you can probably just follow this through with L'Hopital's rule as well. But just by looking at this, similar functions over similar functions, we had a lesson on this in 9.3, I think it was. Comparing rates of growth, these grow at the same rate. So if you compare the ratio of them, it's going to be 1. So all that's going to be 1. So my answer to this limit is going to be x minus 2, absolute value of x minus 2. And that has to be less than 1 for it to converge. So my interval convergence is going to be between, if I add 2, that's going to be 3, and that's going to become, so the other side is -1, so 1. So here's my interval convergence, but I also need to test my endpoints, right? So let's say x equals 1. If I plug in x equals 1, this becomes -1. -1 to the n plus 1 over n times natural log of n. So this is an alternating series, right? So alternating series, I mean, isn't that just what we did up here? Yeah, this we just showed up here. Converges. So converges by the alternating series test. Okay, so we're going to include this right here. let's say for x equals 3. So n equals 3. We have, if I plug in 3, that's just going to become 1 over n times the natural log of n. And hey, this is what we showed in the first part right here. So up here, 1 over n natural log of n, we showed that this diverges by the integral test. This diverges. So diverges by integral tests. So we don't include that. So there you go. There's your interval of convergence. Okay, so I'm going to stop the video there and finish the rest of this in one last video.